Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today our group will present about class AB power amplifier for CD player system. So the question that has been chosen for our group is question number 3. This is our group members, starting with myself, Farrez Irsyad bin Matno, followed by Muhammad AFDHAL bin ABDULLAH, together with SHARIEF bin GHAZALI and MIKHAIL bin Muhammad RAZEEF. So let's get into the project background. So the system that has been shown in the question 3 is the CD driver system. The CD driver system is a system that has been widely used in various technologies such as home theater and also computer technologies. The basic working principle for the CD driver is the driver reads the digital data from the CD, and then the digital data then will be transmitted into the digital to analog converter, which then produce an analog signal of music audio signal. So before this music audio signal can be transmitted to the speaker, it needs to be amplified. So the signal needs to be amplified from the low voltage signal from the driver into a signal with enough gain to be used to power the speaker. So that is the main reason why there is an existence of the power amplifier within the CD driver system. So in this question, we have been used the class AB power amplifier to be embedded into the CD player system. So a little bit about the class AB power amplifier. Class AB is a compromise between class A and class B power amplifier. So class A provides a greater linearity while class B exhibits a higher frequency. So the combination of these two types of power amplifier makes class AB power amplifier a better version of an amplifier. So as we know, class AB power amplifier has a higher efficiency, ranging between 50% to 75%. Class AB power amplifier has also overcome the crossover distortion problem caused by the class B power amplifier. So this has been improved by creating the class AB amplifier by biasing both transistors to be on for more than a half cycle. So on top of that, class AB power amplifier is a greater version from the class A and class B power amplifier, and it is highly suitable to be fitted into the CD driver system.
The next part is connection and operation. So for the connection, from the circuit, the input voltage Vci is connected parallel with both series diode D1 and D2. Besides, R1 is connected parallel to VCC, D1 also with base and collector of transistor Q1. Moreover, R2 is connected parallel to diode D2 also with base and emitter of transistor Q2. The emitter transistor of Q1 is connected in series with transistor of Q2. VCC also is connected with the collector of transistor Q1 and resistor R1. Then, load resistor RL is connected parallel to emitter of diode Q1 and collector of transistor Q2, which both connected in series. To build a complete design of power amplifier, there are few parameters that involve, which is resistor, diode, NPN transistor, PNP transistor, DC source, AC source, and load resistor. And for the operation, from the circuit, a small constant current flows through the circuit of R1, D1, D2, and R2, producing voltage drops, which are symmetrical either side of the input. With no input voltage applied, the point between two diodes is 0 volt. As current flows through the chain, there is a forward bias voltage drop of approximately 0.7 volt across the diodes, which is applied to the base emitter junctions of the switching transistors. Therefore, the drop across the diodes biases the bottom of transistor Q1 to about 0.7 volts, and therefore, the base of transistor Q2 is about 0.7 volt. Lastly, the two silicon diodes provide a continuing drop of roughly 1.4 volts between the two base, biasing them above cutoff. Our project also is based on this Philas table.
For the results, the simulation has been made by using the multisim online software. As you can see, the circuit are showing the class AB power amplifier. So now I am going to show you how the waveform is generated by using this software. But before that, as we all know in theoretical, the waveform of the input voltage should be in the sinusoidal form, while the output voltage waveform should be also in sinusoidal form, but the negative cycle will be cut so that only positive cycle that operates at that time. To prove that, we put the voltage probe at the input here and the output voltage here. Okay, so the input voltage will be green color and the output voltage will be in blue color. Next, to run the simulation, we just simply click the play button here, and then we go to the grapher to see the voltage waveform. Okay, so these are the waveform obtained from the simulation. As you can see, the green line, which is the input voltage, is 6.9 volt and sinusoids. For the blue line, which is the output voltage, is 6.7 volt sinusoids and cut the negative cycle. Hence, the waveform from the theoretical has been proved by the simulation. We go to the next simulation, which is for the output current of the circuit. We take the current probe and put it at the output of the circuit here. We run the simulation again. We go to the grapher. The simulation is running, so we need to pause the current simulation in order to get the value of current by simply clicking the pause button here. Okay, so this is the waveform of the output current, which is 1.1 ampere. Next, to manage the position of the waveform, we can go to the settings, where you can find at the right top corner of the software here. Okay, then you can adjust the the x-axis, which is the time, for example like 0 and 0.03. You can see the changes there. And for the and for the y-axis, which is the amplitude, for example, we place it at -2 and 3. Okay, so that the waveform can be placed at the center of the graph. Hence, this is how the simulation have been performed to obtain the waveform. And that's all from me. Thank you.
And I will explain the results that has been obtained from the simulation, and I will be making comparisons between the values that has been computed from the simulation and the values that has been obtained through mathematical calculation. First, the waveform on the left demonstrates the value of the input voltage Vin of the circuit, which gives the value of 6.9894 volt. But from the calculation, the value differs for a bit, where the calculated value of Vin is 6.928 volt. Then, the waveform on the left is the waveform of the output voltage, Vout. The computed value of the magnitude of the waveform is 6.7102 volt, and the value of Vout obtained from the calculation is 6.928 volt. Theoretically, the value of Vin is equal to the value of Vout. Hence, the value of Vin and Vout are the same using mathematical calculation, which is 6.928 volt. But it differs by a small margin in the simulation, where the value of Vin is 6.9894 volt and the value of Vout is 6.7102 volt. And the third waveform in the middle represents the response of the output current Iout, or also known as load current IL. The value obtained from the graph is 1.184 amp, but the value obtained from the calculation decreases by a tiny margin with 1.155 amp. As I mentioned during the previous slide, there are parameters which can only be obtained manually through calculation. For DC current, input power, output power, and efficiency of the amplifier, there are only their calculated values and no simulated values computed due to the limitations of the software we use in this project, the multisim software. But a comparison can still be done. To find the values of DC current, IDC, and input power, Pin, we need the values of input voltage, and output current. Hence, to make a comparison, we are going to compare the values of input power, output power, and efficiency of the amplifier using the calculated values of Vin, Vout, and Iout, and the simulated values of Vin, Vout, and Iout as the representation for the simulated values of them. The value of DC current IDC when using the calculated values of Vout and Iout is 0.7353 M, and the value of it when using the simulated values of Vout and Iout is 0.7538 M. Next is the output power, Pout. One of the requirements for this power amplifier is to have an output power of 4 watt. Hence, the output power, Pout value, for both calculation and simulation will be 4 watts. And then the input power, Pin. By using calculated values of Vout and Iout, the value obtained is 6.62 watt. And if we use the simulated values of Vout and Iout, we will get Pin is approximately 6.78 watt. And lastly, the efficiency of the amplifier. The efficiency will be around 60.42% if we are using the calculated values of Vout and Iout, and it will slightly decrease to 58.99% if we are using the simulated values of Vout and Iout. To summarize it, there is not much difference between the early calculation values and the simulation values, which indicates that the results obtained from both methods tally with each other, and it proves that the circuit we designed is correct and it computes exactly the values that we expected. The slight margin of differences may be caused by round-up values of the calculation or the internal resistance inside the circuit of the simulation. And most importantly, we were able to design a power amplifier with an efficiency that is in the good efficiency range for the Class AB power amplifier.
So for the conclusion, the operation throughout the experiment was a success where the fundamental knowledge of power amplifier was applied into both practical and simulation. From the early calculations made, it has been successfully implemented into a simulation by using the multi-sim software, where the initial gas calculated by the mathematical calculation approach has been used in order and being compared with the simulation values, and after doing the analysis, both the mathematical approach and also the simulation approach gives up the small margin of error in the term of values. So that proves that the research and the initial guess from our mathematical equation was right. And finally, the Class AB power amplifier with the output power of approximately 4 watt of a CD player system successfully designed. Thank you.